Electronegativity is a periodic property of the elements, and this term refers to the ability of an atom and specifically an atom in a molecule. So it's a property of atoms within molecules and refers to the ability of that atom to attract the electrons within its covalent bond to itself. So electronegativity refers to when an atom's ability to sort of share unequally the electrons that are in a bond, and that results in polarity for a covalent bond, and which we will discuss. So, for instance, just to refresh your memory, covalent bond refers to a sharing of electrons, which allows the atoms to complete their valence. So, for instance, two hydrogen atoms, each one wants to have an extra. They each have one electron, so they need one in order to complete their valence shell. So, if they share electrons by forming a covalent bond, now each hydrogen atom has a complete valence of 2, which we call a duet for hydrogen. Those two dots we represent as a line to indicate a 2-electron bond, in which, of course, 1 electron came from each atom. Now those electrons in the bond we consider to be evenly distributed between the two hydrogen atoms. And the same can be said for a covalent bond between two fluorines. So fluorine has 7 valence electrons and therefore needs one more to complete its valence of 8 electrons. So if I combine these two fluorines to form a covalent bond, now sharing those 2 electrons, they've each completed their valence shell, forming a 2-electron bond, and those electrons are considered to be evenly distributed between the two fluorines. However, what's found is if we bond together two unlike atoms, so in other words, two atoms which are not the same, the hydrogen and the fluorine, now by sharing electrons, the fluorine can help hydrogen complete its valence shell of 2, and the hydrogen can help fluorine complete its valence shell of 8, forming a 2-electron covalent bond, which we represent with the line. However, the electrons in that bond are not evenly distributed between the two atoms. In fact, the electron density is centered more on the fluorine. So the electrons have a higher probability of being closer to the fluorine atom than they do to the hydrogen atom. And the reason for this is that the fluorine has a stronger ability to attract those electrons to itself in covalent bonds, stronger than hydrogen. And so fluorine essentially does not share equally. It pulls the electron density from the bond closer to itself, and in fact this results in an uneven charge distribution. Electrons are negative, so pulling electrons towards the fluorine results in a slight positive charge around the hydrogen and a slight negative charge on the fluorine, which we represent with these Greek symbol delta to indicate the partial positive and partial negative charge, and to distinguish it from the full positive and full negative charge which we would write on ions. So you can see this molecule has a negative side to it and a positive side to it due to the polarity of the bond. And we represent the polarity with an arrow drawn towards the side with the negative charge. And so this HF bond is polar towards the fluorine atom. This concept of electronegativity was And this polarity results in what we call a polar covalent bond. Now, the idea of electronegativity and polar covalent bonds was first proposed by Linus Pauling, a very famous and influential chemist who actually won the Nobel Prize in Chemistry and Peace, one of the only people to win 2 Nobel Prizes by himself and in 2 different categories. And Pauling used this idea of electronegativity to explain the difference in bond energies for the HF bond compared to the hydrogen-hydrogen bond and fluorine-fluorine bond. In other words, one might expect the bond energy for HF to be an average, right, of the bond energies of the hydrogen-hydrogen bond and the fluorine-fluorine bond. However, if you look at the bond enthalpy for the hydrogen-hydrogen bond, we find that it's 436 kilojoules per mole. In other words, it takes that much energy to break the bond. The fluorine-fluorine bond, 155 kilojoules per mole. But the HF bond is 567 kilojoules per mole. So it's much stronger than one might predict based on the bond strength of the So its bond strength is much stronger than one might predict based on the hydrogen-hydrogen bond and the fluorine-fluorine bond. And Linus Pauling explained this increase in the bond energy for HF and other molecules composed of unlike atoms by saying that it had a partial ionic character. So it is a covalent bond, but because of the uneven distribution of the electrons, you get a partial negative charge and partial positive charge on opposite sides of the bond, and this results in a partial ionic character of the bond. And therefore we call this not just simply a covalent bond, but a covalent bond with partial ionic character, or simply a polar covalent bond. Now, as I pointed out earlier, electronegativity is a periodic property. If we look at a periodic table, and this is color-coded with the darker orange meaning more electronegative element, and the lighter yellow color less electronegative element, we see that electronegativity in general increases up the groups and across the periods. And that results in francium being the least electronegative element, and then fluorine being the most electronegative element. If we look at another type of another bond, like between carbon and fluorine, and we want to know if this is a polar bond, we can simply look at their position on the periodic table. Fluorine is much further to the right than carbon, and so we know that they have a difference in electronegativity just based on their position in the periodic table. And so since fluorine is further right, we know it's more electronegative, and therefore has a stronger ability to attract the electrons in that 2-electron bond to itself. So we expect, based on the higher electronegativity of fluorine, that the carbon-fluorine bond will have a dipole moment towards the fluorine, with a partial negative charge on the fluorine and a partial positive charge on the carbon. We can actually calculate the difference in electronegativity simply subtracting the electronegativities of the two atoms using the Pauling scale for electronegativity. Those are the numbers below the elements in this periodic table. If we look at the Pauling scale, we see that fluorine has electronegativity of 3.98, carbon electronegativity of 2.55, for a difference of 1.43. In general, you can just use the position on the periodic table to determine if a bond is polar or not. However, sometimes it is useful to actually look at the difference in electronegativity to judge how polar a bond is, or to categorize it. So for instance, if we want to know something about the bond character, for instance, if it's going to be a strictly covalent bond, nonpolar, a polar covalent bond, or if it's actually ionic, we can use the difference in electronegativity to get an estimate. And so electronegativity difference, and we use a scale, generally, roughly, a scale of 0 to 0.3 or 0.4 is considered strictly covalent. In other words, that's not a big enough electronegativity difference to call the bond polar. 0.4 to 2 is considered a polar covalent bond. So if you have a covalent bond and the electronegativity difference between the atoms is between 0.4 and 2, then it is considered to be a polar covalent. If it goes above that, then the atoms will likely transfer electrons and you'll have an ionic bond. So, for instance, in the carbon-fluorine bond, we saw that the electronegativity difference was 1.43, and so this is described as a polar covalent bond based on that electronegativity difference. If we look at carbon and hydrogen, based on the Pauling scale, carbon 2.55 and hydrogen electronegativity of 2.20, that's only a difference of 0.35. And so the carbon-hydrogen bond, you can see, is just covalent. We don't consider that to be a big enough electronegativity difference to call it a polar bond. In fact, we call it a nonpolar bond, or just strictly covalent bond. And then finally, let's look at the other extreme, lithium to chlorine. This results because chlorine has an electronegativity of 3.16 and lithium 0.9. This results in a difference in 2.18, and then so based on our table, that's above 2.1, and so this we would predict would be an ionic bond. And in fact, that is the case. We know from that lithium chloride is fairly readily dissolves in water, and which is a pretty good indicator of ionic character.